AP Calculus BC, Day 8, Section 1, Office Hours. These are the even answers. The odds are in the back of the book, so you should check those in the back. So you can pause the video right now if you need to check these answers. And let's go over them. So, first problem, number 1, says to replace the asterisk with an expression that will generate the series. So they give you this series, which I would write down. So write the problem down. And so A says, they give this to you all done. And you're supposed to put something here that will make it work. So since they're starting at n equals 1, I think we should go with n equals 1, n equals 2. So I always find it helpful to write these next to the terms to kind of figure out what the pattern is. So we're going to have an alternating negative, which is already taken care of with this, which that looks right. N equals 1, negative 1 is 0. It's going to be positive. On the bottom, though, it's going to have 2 squared, 3 squared, 1 squared, 4 squared. So it should be n squared. That is what you should add to that term. Okay? B, this one starts at n equals 0 and has very similar stuff. Now, the negative 1, since we're starting at 0, would make sense. You could put zeros here if you want. 0, 1, 2, 3. That's good. But now it needs to be n plus 1 squared. So n plus 1 squared should be what you add to this to make it work. Okay, C, n equals, you're trying to decide what to start it off as negative 1 to the n, negative 1 over n minus 2 squared. So we want to get a 1 here under the first one, so I think we'd put a 3. But, I mean, I guess it could also be like a 1 and still turn out positive. But the first term has to be positive. Put a 3 here. I don't think that's going to work. 3 minus 2 squared, that'd be 1, 4, 5. So I feel like we would start with 3, but there's an extra negative here. So that's why it's going to work. Negative 1 to 3 is negative 1, but then there's always this extra negative 1. So the answer is 3. Okay. Number 2 says write an expression for the nth term, and they're calling a to the n. So A, they give this to you. You should write this down. So you're trying to figure out what the nth term is going to be, and they're calling it a to the nth. So we got to figure out the pattern here. Now, this looks like a geometric series. We're multiplying by 1/3 every time, and we're starting with 1. I think if we did 1/3, now you're stuck with whatever they say the starting n value is. So I think it would be 1/3 to the n. That's what you would put there, right? B starts at n equals 1, so we got to pay attention to that. Now, I noticed the terms are flipping signs, so we definitely need like a negative 1 to a power involved. Definitely need a negative 1, and it'd be like n minus 1 or n plus 1. That's up to you. or actually n minus any odd number, n plus any odd number. You want this negative to be raised to an even number on the first one, and then odd, then even. The most direct one be n minus 1. This is 0 power. Now that takes care of that. The denominator is increasing. If you write this below it, n equals 1, n equals 2, n equals 3, n equals 4, you'll notice that the denominator is just whatever the n value is. So we could just say over n. Now, like I said, you have a little bit of room to change the n minus 1 on the negative 1, but this has to be n. Okay, C. So there's clearly a pattern here. I mean, I might reinterpret this as 5/10, 5/100, 5/1000. I feel like it might be easier. Tenths, hundreds, thousands, 10,000s. Okay, they're all the same sign. They all have a 5, so there's just a 5 there. And then this is like 5/1. So this is like 10 to the 0, 10 to the first, 10 to the second. Now we're starting at n equals 0, which seems nice. So it's going to be, I think it's going to be at 1 over 10 to the nth power. So, all right. Just getting good at seeing the patterns there. Number 3 through 6, it says, tell whether the series is the same as this series. N equals 1 to infinity of negative 1/2, n minus 1. So, I mean, you could write some of the first terms out just to help you. I mean, when n equals 1, it's to 0, so that's a 1. Plus, when n equals 2, it's going to be negative 1/2. When n equals 3, it's going to get squared. It's going to be 1/4. When n equals 4, it's going to be cubed. It's going to be negative 1/8. So you can see a pattern here. So we're going to look for other ones that give us the same pattern. First of all, it's definitely going to start positive, then negative, then positive, negative. And it looks like a geometric series multiplying by 1/2 every time. So if they don't have the positive negative pattern, then they're for sure, we could rule them out. So number 3, this is for the next 4 problems. Number 3, I mean, you could just start writing it out if you want, but you know, so if you plug 1 in, that's going to be negative 1. Well, that one's out. This is different for sure. In fact, all the terms are going to be negative. I mean, that's a giveaway. I mean, the first term is negative. It should be positive. All the terms are going to end up negative because they all have a negative in front. You know, if you do n equals 2, it's going to be negative 1/2. You do n equals 3, it's going to be negative 1/4. So it's close. It has all the numbers, but it doesn't have the negative positive pattern correct. So it is different. Next one. Now, you could just start writing terms out if you want. The first term is positive 1. Next term is negative 1/2. Next term is positive 1/4. This seems to work. I think this is the same. You could also think, could I rewrite this? Since we're starting at 0, the only difference between this and this is that power, and you just want to make sure you have a 0 power in the first one, and these do the same thing. Okay, number 5. I mean, you could just look at these and say, n equals 0. I mean, this is just like the last one. They've just separated the negative and the positive, the negative and the 1/2, but they're both to the 1. I mean, you could rewrite this as negative 1/2 to the n just by using rules of exponents. These are the same. This is the same as the last one, which was the same as the original one. Okay, 6. This one, if we just start plugging in terms, if you plug in a 1, you're going to get -1 right away in the first term, which is wrong, right? It's different. Who cares or who knows how close it is? But I mean, if you plug in n equals 2, you get +1/2, and then you plug in n equals 3, you get -1/4. So it actually has the same pattern, but the pluses, minuses are in the wrong places. So that's 3 through 6. 7 says, compute the limit of the partial sums to determine whether the series converges or diverges. So, whatever algebra technique you want to use, 1 plus 1.1. So you want to do the partial sums. You're gonna slowly add them up and see if you can distinguish if something's happening. So the first partial sum is 1. The next partial sum is 2.1. The next partial sum is, you add this to that, it's 3.21. The next partial sum, you add that, it's 4.321. The next partial sum, you add that, it's 5.4321. So there's a pattern going on, but these are going to get, the partial sums are getting bigger and bigger and bigger. The terms are getting bigger, right? I mean, that's really more the thing. The term, every next term is bigger than the last. It's increasing by bigger amounts every time. The terms have to be smaller for it to even converge. So this would diverges. Okay, 8, 2 minus 1 plus 1 minus 1 plus 1 minus 1 plus ... Just start writing the partial sums. The partial sums, the first partial sum is 2. The next partial sum is 1. The next partial sum is 2. The next partial sum is 1. The next partial sum is 2. The next partial sum is 1. There's a pattern. It's not going to a certain value, though. It's not going to blow up, but it's not going to a certain value, so we say it diverges. Okay, number 9. 1/2 plus 1/4 plus 1/2 plus ... plus 1/2 to the k. So giving you the general term. Okay. So the terms are getting smaller. That's good. It's not enough. I mean, you can start writing the partial sums. 1/2 plus this would be 3/4 plus this would be 7/8. And so it looks like it's going towards 1, towards value of 1. This is a geometric series, by the way. And the A value is 1/2. The R value is 1/2. You could do your test. Is the absolute value of R less than 1? Yes, it is. So it does converge. It converges. And they did ask you, they just said whether it determines converge. So it converges. And that's all they're asking. We could go ahead, because it's a geometric series, we could go ahead and compute what it converges to. It's A over 1 minus R for geometric series, 1/2 over 1 minus 1/2. It goes to 1. Not that they asked you to on this problem to do that. Okay, number 10, same kind of problem. 3 plus 0.5 plus 0.05 plus 0.005 plus 0.005 plus ... So sometimes it could just be a random number in front. You can kind of ignore that. Now, we are supposed to write the partial sums. I mean, the first partial sum is 3. And I think sometimes it's easier to work with fractions. I think I did that on another problem at some point. So, I mean, we can cut, the 3 doesn't really fit the pattern, but that's fine. You can just have a random number. That's not going to change whether it converges or diverges. If you just add a number to a number that converges, it's still going to converge. The first partial sum is 3. The next one is 3.5. The next one is 3.55. The next one is 3.555. The next one is 3.5555. And so it's clearly going towards a specific number, right? The sums, they're getting a little bigger, but it's it's not blowing up. It's increasing by smaller amounts every time, and it is approaching a certain value. Like I would say that I would predict that this converges, and it converges to 3.5 repeating, right? Now, just taking a different approach, it does seem to be approaching that. You could write the, n equals 3.5 repeating. You can multiply by 10. And then you could subtract n. And we could get a fraction for the answer. So 32 over 5 is 3 5/9. I mean, that is also another version of it, using that trick from Calc AB. We could treat it like a geometric series. This is a geometric series. You would find the sum of this part separate from the 3. So, you could say, okay, well, this is, we could even write the closed form if you just want some practice with it. By the way, the last problem, if we wanted to write the closed form of this is just all good practice. This is a challenge, so you might as well take advantage of it. We could say n equals, 0 or 1 or whatever to infinity. And it's 1/2 to the n plus 1, right? I mean, that's the closed form of this one. This one, it'd be 3 plus the closed form. Now here, if you look, you could say this is your first term, a equals 5/10, which is 1/2. And r equals 1/10. We're multiplying each term by 1/10 to get the next one. So we could say, all right, n equals 0 to infinity. First term is 1/2. Then you multiply by 1/10 to the n power. So that would be the closed form of it. But you could say, okay, absolute value of r is less than 1, so it converges, right? And then we could use that formula. The sum equals a over 1 minus r. A is 1/2. R is 1/10. And you get 5/9. Now you buy, but I thought it was 3 5/9. Well, I can only apply this formula to the geometric series part of it. So then you would add 3 to it, and you would get the same answer we got the other way. So a few different ways to deal with this. It's good to try these. Okay. Problems 11. Okay, so 11, same kind of problem. Well, it says tell whether the series converges or diverges. If it converges, give its sum. All right. So let's see. 11 is 1 plus 2/3 plus 2/3. squared plus 2/3 cubed plus dot 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 plus 2/3 to the nth. So this is the open form, but it does have the general term there, which is all you need usually for the closed form. But we're multiplying by 2/3 every time. This is a geometric series, right? And you're supposed to decide if it converges or diverges, and if it converges, what does it converge to? So the R value is 2/3, and the absolute value of it is less than 1, so it converges. So then you'd find the sum, A over 1 minus R, which I'm going to write every time for a while until I get it really good in my head. This is the A. R is 2/3. So it converges to 3. That's the sum of the series. If you were to write it in closed form, just for practice, you would say you could start at 0 or 1. It's up to you. And we could say, okay, 2/3 to the n power. That would totally be the closed form of that. Okay, 12. 12 is 1 minus 2 plus 3 minus 4 plus 5 minus dot 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 plus -1 to the nth n plus 1. So I don't know. I don't think this is geometric. So I'm going to use a different approach. I can't use I can't say, well, this is the R value. So because we're adding 1 every time, right? Adding 1, adding 1, adding 1, which that's that part. And then we're changing the sign back and forth. That's that part. So in closed form, this is n equals, it's just going to have this stuff in it. -1 to the n plus 1 to infinity. You got to decide what value n to start with to make sure that it gets the right size. So n equals 0. So that's the closed form of it. That doesn't tell you if it's convergent or not. So I'm going to do the partial sums. I feel like that's my best way to see what's happening. So the first partial sum is 1. Next one's -1. Next one's 2. The next one's -2. Next one is 3. And then if you subtract this, you get -3. So I think you could see a pattern going here. The partial sums are getting bigger and bigger and bigger. This for sure diverges. Okay? For sure diverges. And the partial sums are good defense of that. Okay, 13, n equals 0, infinity, 5/4. Now, you need to start recognizing, hey, that's a geometric series. Whatever the n value is gives you another 2/3, another 2/3, multiplying it by another 2/3, right? So this is a geometric series. And when n equals 0, that term goes to 1. So this is your A value, and this is your R value. So A equals 5/4, R equals 2/3. The absolute value of R would be the absolute value of 2/3 is less than 1. So we know it converges, right? And then to find the sum, we're going to do A over 1 minus R. So 5/4 for 1 minus 2/3. 5/4 over 1/3. 5/4 times 3 over 1. 15/4 or 3 3/4. Whatever. Okay. All right, 14. One more of these. You could start writing the terms out, the open form. But like I said, you need to recognize this is a geometric series. The only thing that's happening is that each term is getting another 5/4, another 5/4, multiplying it. That is what a geometric series is. And once you know it's a geometric series, then you can use some of these things that we've talked about just to figure out. So if n equals 0, the first term is 2/3. Next term is going to be 10/12ths, right? The next term is going to be 50/48ths. You don't need to do that, but that's what's happening. But the first term is 2/3. The R value is 5/4, the thing that's getting repeatedly multiplied. The absolute value of R is the absolute value of 5/4 is less than 1. This is the kind of work I want you to show to convince me you understand why it converges. In your next test, this is the kind of work I need. I need that. The sum is A over 1 minus R is 2/3 over 1 minus 5/4 is, oh shoot, hold on, no, crap. This is bigger than 1, so it diverges. And we're done. Don't even use this formula. It diverges. I was just kind of mindlessly going through it. Okay. Let's see. A few more problems. 15. Now these problems say same. Okay, so these next couple are still the same kind of problem as before. So this one's kind of interesting looking. N equals 0 to infinity cosine of n pi. And I'd just start writing down the terms. When you put 0 in, cosine 0 is 1. You plug in 1, you get negative 1. When you plug in n equals 2, you get cosine 2 pi is 1. You plug in 3, cosine of 3 pi is negative 1. So I think we see the pattern here. Now, we could write this a nicer way because it's just ones and negatives ones. I mean, it's really just negative 1 to the nth power, right? Isn't that it? Doesn't that give you the same thing? Right? Or you could start at 1 if you want. Do negative 1 times n minus 1. That's the same thing. So by the way, this is a geometric series. I mean, we could take that approach. If you realize that this is a geometric series, we're just multiplying by negative 1 every time. The A value is 1. The R value is negative 1. The absolute value of R has to be less than 1, and it is not, so it diverges. So you could use that approach. You could look at the partial sums and see what's happening. In partial sums, first one's 1, next one's 0, next one's 1, next one's 0, next one's 1, next one's 0. Are they going towards a certain value? No, diverges. So, but it's interesting that it was a geometric series, kind of in disguise. 16, 3 minus 0.3 plus 0.03 minus 0.003 plus 0.0003 plus ... and they give you the general term, I think, 3 negative 1.1 to the nth power. Okay, so, I mean, just looking at this, the general term, that's a geometric series. There's a number that's being raised to a power, which means you're getting that extra number every single time. So the A value is 3. The R value is negative 0.1. And so the absolute value of R has to be less than 1, which it is. So this converges. And so the sum equals A over 1 minus R equals 3 over 1 minus negative 0.1, which is 3 over 1.1. Which we could, you shouldn't have decimals in your fraction. So we can multiply top and bottom by 10. And there's the answer, or 2 and 8/11ths, whatever you want. So there it is. Okay, 17. Wow, this one looks crazy. Okay. Wow. Well, can we now? I don't know. Like I look at that and I don't think, oh, that's a geometric series. I'm like, I don't know what's going on. Like I think we should just start plugging some values in. N equals 0. Sine of pi force would be root 2 over 2, right? Or, but then it gets raised to the 0th power, right? And then the next one, n equals 1, that's going to be 5 pi over 4. That's third quadrant, so it's negative, and it's going to be root 2 over 2, and then it's going to get raised to the first power. And then the next one, you plug in a 2, you're back in the first quadrant, so you get root 2 over 2 squared. I mean, I look at that and I'm like, hey, I keep seeing a root 2 over 2 to a higher and higher power. This is the same thing. This is a geometric series. And this one's 1. That's root 2 over 2 raised to the n power. I'll actually put a negative in there so that it'll flip signs. They're the same thing. And this is a geometric series with an a value of 1 and an r value of negative root 2 over 2. Now we need the absolute value of r to be less than 1. Is root 2 over 2 less than 1? Well, root 2 is like, it's less than 2. It's like 1.7 or something. So this is true. It does converge. It converges. The sum is a over 1 minus r. So a over 1 minus negative root 2 over 2. So we're going to clean this up. I don't want a complex fraction. So that's going to be plus. We could give this the least common denominator. We could multiply everything by 2. So it'd be 2 over 2 plus root 2. That's sort of a nice version of that answer. Okay. All right. Let's see. Did I do that right? Seems right. Now you could do other things. You could simplify, or you could rationalize the denominator by multiplying by the conjugate if you want. I don't know what the answer in the back of the book was for this. If you do that, you get 4 minus 2 root 2 over, this would be 4 minus 2, so you get 4 minus 2 root 2 over 2. So you get 2 minus root 2, which I think that's the answer in the back of the book. So there you go. That's how you can get the answer back. These are the same. Okay, 18. 1/2 plus 2/3 plus 3/4 plus 4/5 plus plus n over n plus 1. They give me the general term. Okay, so is this a geometric series? We're adding 1 to the top every time, and we're adding 1 to the bottom every time. Adding. And it's not arithmetic because we're not adding a one number to 1/2 to get 2/3 and the same number to 2/3 to get 3/4. The pattern, if you'd write as a closed form, I think it would be 1 plus n, if we start at n equals 0, over 2 plus n. And that's a closed form. It's not geometric. It's not arithmetic. I think our only tool at this point is to investigate the partial sums. First of all, the terms can't be getting bigger, which they are, so that's bad. But then you can make it obvious. 1/2, if you add that, least common denominator would be 3, 4, 7, 6, and then you add 3/4 to that, and 14 plus 9 is 23. 12. I mean, this is getting bigger. It was 1/2. Now it's bigger than 1. Now it's almost 2. Like, it diverges. Okay, it diverges. Assuming I did that right. 3 plus 4 is 7. Yeah, that looks right. Okay. All right. 19 has n equals 1 to infinity of e over pi to the n. Okay, that's a geometric series. You're raising some number. E over pi is just some number over some other number. It's ugly and messy, but it's just a number to a power. This is a geometric series. So you wanna recognize these. When you plug n equals 1 in, that's the a value. That's the first power. E over pi. R equals E over pi. So some of you guys may mistakenly think, oh, A equals 1. If n equals 0, then yeah, A would equal 1. But n equals 1 is the first term. Whatever n equals here, that's the first term. So then you need to say, okay, well, is the absolute value of R, E over pi, is that less than 1? Well, E is like 2.7 and pi is like 3.1. So yeah, it's less than 1. So it converges, which is one thing you're supposed to. And now the sum is A over 1 minus R, E over pi over 1 minus E over pi. Let's clean this up. I don't want complex fractions for sure. Give at least common denominator. So you have E over pi minus E over pi. So we could get rid of the pi's and get E over pi minus E. Okay. All right. Last one. 20. They're giving it a closed form. Now, I don't know. I mean, I don't think that looks like a geometric series. Now, if you start writing terms out, it might start to shed some light on it. If you plug 0 in, you get 1 over 6, right? Then you plug 2 in and you get 5. I'm sorry, you plug 1 in and you get 5 over 36. And then you plug 2 in and you get 25 over 216. Now, if you look at this, this is a geometric series. We're multiplying by 5 over 6 every single time. 5 over 6. This is a geometric series where A equals 1/6 and R equals 5/6. Now, you could write this a little more like a geometric series where you'd be like, oh, well, the first term is 1/6 and the R value is 5 over 6. We're going to raise the n power. This is the same thing. And that looks a little more like the way we might write a geometric series to start with. So is the absolute value of R less than 1? Show this. Write this in your work. Okay? Because I'm going to require that to know. You can just guess if it converges or diverges. 50-50 shot. I want to see why you think it converges. This is the why for geometric series only. Okay? The sum is A over 1 minus R. A is 1/6. R is 5/6. And this one converges to 1. Kind of nice. All right, that's it. Have this done before tomorrow's lesson.